Hello there. This is Answer Everywhere. We are doing a live show, which is improvised, and we're taking a look at Apache Spark. So, I know Apache Spark is super popular. So, just to set some, I guess, expectations, this is about doing. This is more like a journal reading club or a book reading club than it is like a tutorial on how to use something like Spark. So the theme of the show is I'm coming in with no real context about the source code of Spark. I haven't even used Spark myself, so I have less context, I think, than some of the users. But the goal is to try to understand the code base as if we were wanting to contribute to it, and we needed to dig around and see where things were and see what the truth of how Spark works is compared maybe to some of the documentations or some of the tutorials, which simplify things and maybe provide an extremely useful but slightly different perspective than you would get if you look directly at the code. So that's what we're doing. Apache Spark is huge, and just in the interest of going straight for the jugular, I think what I want to do is look at the RDD code, because I think there's an important sense in which Spark is oriented or organized around the RDD abstraction. So let's do that. In terms of background, we have looked at a few similar or maybe semi-related repos on the show before. We've looked at databases like Postgres. We've looked at graph databases like Neo4j. We've looked at distributed systems, things like gRPC, Cilium, Kubernetes, eBPF. So I'm going to assume just some basic familiarity with the concept of a distributed system. I'm going to assume some basic familiarity with the idea of how a database works. And that will allow us to essentially go for the diff between what we've done before and what Spark is about, which is, I think, fundamentally about providing an abstraction layer for you to have distributed data jobs. And the way that abstraction layer is provided is through this RDD mechanism. So let's see if we can find an architecture diagram that's reasonable. These are kind of like the entry points for the programmer that supports SQL. Streaming, I'm not sure I remember exactly what it is. GraphX is some kind of distributed graph database, and mlib is for machine learning. But what I want is maybe something with here we go. So the way that it works, my understanding at least, is there's some driver. You essentially initialize a context, or I think maybe in newer versions it's called like a session, and you have essentially a traditional distributed systems machine architecture where you have essentially one leader or master or driver is maybe what it's called. I'm not sure if it's called the driver, but then you have a bunch of workers. And so it's the job of the driver, I think, or the organizing machine to tell the workers what to do and also keep track of where all the data is. So you might have too much data to fit on a single hard drive. In fact, that's the typical case. And so the data may live, I guess, on each of the workers. It may live in some data pool somewhere. But it's Spark's job to figure out where is the data, how do we organize it so that when you write your computations, you don't have to worry about fetching the data, and how do we do that efficiently? And so RDDs are the way that they are essentially the main abstraction for doing that data bit and distributing the computation. And then they're going to build some DAG, so directed acyclic graph. We've seen this a bunch of times in different settings, but the directed acyclic graph represents which computations essentially depend on which others. And you need to know that you need to be able to build that to do like a topological sort so that you run the computation that the thing that's dependent on the most, essentially you run first, and you need to run that before the stuff that depends on it and so on. So those are in my opinion, the core components. And then we have a bunch of stuff that's, I guess from our perspective, we're going to consider a little bit like implementation details. So there will be an abstraction layer over, you can use Yarn or you can use Kubernetes, I think, but you have some way of, Spark isn't in charge of like running, it isn't in charge of making your cluster of computers in general look like a single computational engine. That's offloaded to something like Kubernetes. And then we don't really use the word slave anymore. But these are workers. And I guess the executor is maybe the thing that is organizing the computations. We'll spread the workloads to the workers, and they have some cache, which I think is largely in memory cache. And they have tasks that they execute, and then you write to some distributed file system, perhaps. So that's the main thing, and we're going to just focus kind of here on whatever this shade of green is, the RDDs and maybe the DAG scheduler, but I'm not sure if we're going to get to the DAG scheduler. So we started a little bit late. One second, and so I'll probably go a little bit late. So the next stream, which is on MySQL, will probably start later than expected, but I want to at least get a fair understanding of what the RDDs are about. And maybe one more thing. Let's see if we can find a diagram that just discusses the RDDs. I'm not sure which of these is going to be potentially interesting, so I guess we'll ignore that. But we will ask Bard, tell me about RDDs in Spark, and we'll kind of let it think about that while we open up some files. So core is, I'm sure, where everything is going to be. We are written mostly in Scala, which I do not read, but I'm hoping it'll be close enough to other functional languages or to the other JVM languages that I have used that we can make some sense of it. So I'm going to guess Scala/org as opposed to Java.org is where the money is. The protobuf might be interesting, so I'm going to open that. That might be an important source of information about the API. The folders here are well named. Executor is presumably going to be the thing that executes and organizes the computations. I will open this. I probably will not get to it, so I guess I'll pull it into its own browser window here. And then RDD is the main place I want to be. RPC is presumably going to be remote procedure calls, ways for the different machines to talk to each other. Metrics is going to be, I think, like metrics, things that you want to measure so that you can optimize your execution or maybe tune your deployment of Spark. Broadcast is presumably going to be how machines send information to each other. And scheduler, I think, might be interesting. Shuffle, I think, is fundamental based on like the talks and the documentations I've seen. What shuffle is essentially is when so you say you need some you tell Spark that you have some computation that's going to need, let's say, like the names of all the people in all the states, and maybe each machine has information about like a third of the states. So somehow Spark has to make a decision about where to load all of the memory, and necessarily that involves pulling memory from different machines and organizing it somewhere to co-locate it with the computation. And that reorganization is what they call the shuffle. And that's one of the most resource-intensive parts of Spark, from what I'm seeing from people who use it. So you typically want to minimize the amount of shuffling because there's a sense in which that's just wasted work. And then here in the main directory, not in any of the subdirectories, we have a bunch of stuff. And I'll just see if there's anything RDD looking here. I imagine usually the stuff in the main directory is going to be important. But just in the interest of quickly getting to where we can get to, I don't want to focus on everything. But we see things like heartbeat. Presumably, I guess this is going to mean that machines send like "I'm still alive" style heartbeats, and the executor may use that to determine whether workload or something or a task or a worker node is in trouble. But I don't see anything that looks super RDD-ish. Maybe I'll just do a search. We have the RDD folder, and really that's it. All right. Okay, so here's protobuf. One second here. All right. So protobuf should hopefully tell us about some interesting things. We have stored, it's called store types. Do we care about store types? I'm not sure. We have like an enum for the like job execution status, job data. And interestingly, all the protobufs are int64, even though sometimes the corresponding types are int32 in Spark. And that's, I guess, so that they can use the same, if they decide at some point that something needs to switch to int64, they can use the same protobuf. Stuff like job data wrapper, task data wrapper, I guess it makes sense that these are things that information about jobs are things that the executor will have to tell the workers about. Before I get too deep here, let me make sure that executor is the right word to call this thing. What is the relationship between worker instances, and executor? There's a master node and worker nodes. Yeah. But is executive the same as executor? I'm not sure. Do they call it master? Spark jargon. Okay, no, they're not called executor. An executor is a process launched for an application on a worker node that runs a task. I think maybe they just call it master. All right, I'll call it master, I guess, even though that's not the cool way to talk. Let's see, what's the master machine called in Apache Spark? Is it just called master? Or is there another name? The Spark master. All right. And we have some information about RDDs. We'll come back to that when we get to the RDD file. Where did protobuf go? Did I close it? I think I did. Okay. So here's the RDD directory. What is this? This is shuffle. I guess we'll pop shuffle out into its own thing. We probably will not get to shuffle. And I'm not sure the right way to go about RDDs. So one way is RDD.Scala is presumably going to do things like define the interface or an abstract class or something like an abstraction that all of the other RDD implementations depend on and extend in some way. But it might be useful to pull out some examples of RDDs and see what their implementations look like. So how about JDBC? So JDBC should be the SQL abstraction layer for Java, for the JVM. We have async RDD actions. So these may be like utilities or actions for the RDD rather than an RDD itself. We also have binary file and block. Cartesian, I'm going to guess this is like the product of two RDDs. Maybe checkpoint. We'll just pull a few of these and take a look at them and see whether there's something unique about those. So we also have subtracted and union. So maybe union will be like the union of two RDDs. There seems to be some sort of algebra of RDDs potentially based on the naming I'm seeing. And then subtracted might also be like this part of the RDD, but not that part. Like maybe we need the first 10 items of some RDD or something like that. So I guess that'll be good. So in the first tab here, we have RDD.Scala, which is just how many lines of code? Around 2,200 roughly. So we'll kind of go from the right hand end here and see how that goes. Let's look at one RDD and then see what Bard has to say. And I think maybe the RDD I want to look at first is the SQL one, which is called JDBC. And this is 226 lines. and that's not big. So we have this I don't want. Can I get rid of this? This, go away. Like that, right? But I maybe want this thing over here. Okay, so we have job partition, which is a private class. I don't know what this Spark annotation is, but there's some sort of Spark annotation. So we have a JDBC partition is the class, and it has an index. A values for, val is just, I think, a keyword in Scala that basically says a variable that you can assign to maybe, or maybe it's immutable, like Kotlin or whatever. But we have longs for the lower and upper. Lower and upper. What? Maybe indices? Maybe rows? I'm not sure. But this somehow specifies a partition. And we're overriding the index to be to return, I guess, the thing that you pass in here or something. And this may just be setting a variable in Scala. I'm not sure. I'm not sure what override is doing here in particular, but it should be, yeah, it's a def. So I guess it's a function. And we get a comment here, an RDD that executes a SQL query on a JDBC connection and reads results. For usage examples, see test case, JDBC RDD suite. So looking at tests would be another really excellent example to figure out how this stuff is used. But that is something that typically I would do in a professional setting. But again, in the interest of time, so that we can see the actual implementations quicker, I'm going to skip the tests for now. So here are the things we can do, or rather, we have a parameter get connection, which is a function. So we're in Scala, so I guess the idea is that we can pass functions as values. So you pass in a get connection function, which is a function that returns the open connection, and the RDD takes care of closing the connection. SQL is the text of the query. So I don't know if it's in a string or if it has some SQL type. It must contain 2 question mark placeholders for parameters used to partition the results. Okay, so for example, select title author from books where question mark is less than or equal to ID and ID is bigger than or equal to question mark. And I guess the idea here is that maybe that's where lower and upper come in. But the idea here, I guess, is that Spark is going to take care of taking your query and adjusting the indices so that they match maybe the rows that are available in the different worker nodes, so that it can call this with different instantiations of the question mark potentially, and then aggregate the results in some way. And then we have lower bound and upper bound, which are the minimum value of the first placeholder and the maximum value of the second placeholder. So minimum on the first one, maximum on the second one. That makes sense because you have an interval and you're basically how big is the interval. Num partitions is the number of partitions. Given a lower bound of 1 and an upper bound of 20 and a num partitions of 2, the query would be executed twice, one with 110 and once with 1120. And then map row, you're passing in, I guess, another function. And this is a function from the result set. So the result set is presumably what the SQL query is going to return on each of the in each of the tasks, to a single row of the desired result type. Okay? To a single row. From the result set to a row of the result types. I'm guessing maybe the row is, I don't know what it means by row, but we'll see. This should only call get int, get string, etc. The RDD takes care of calling next. The default maps a result set to an array of object. I don't know if this is saying to return, if this is like the way of aggregating the different results or what, but maybe we'll see what's going on. And then we have this class, which I'm not really sure to what extent Spark classes differ from Java classes, but I guess we'll see. And the JDB, the class depends on this. I assume this means it depends on a type, which is a class tag. And and you pass it in a Spark context, which is, I believe, kind of like a global configuration object. We saw it in one of the diagrams, but basically it's like a context for all of the work that you're doing that you create as one of the first things you do when you start a Spark project. And then you pass it in this get connection thing, which will return a connection. And you pass in the SQL string, the SQL query as a string with some question marks in it, the lower and upper bound, the number of partitions, and this map row, which takes a result set and sends it to, I don't know what this T equals syntax is, but something about a result set to object array. I guess this is the default implementation. But in general, map row is going to take a result set and return a T, which was the thing that this class depends on. And it's going to extend RDD of T with the Spark context in nil. And with logging presumably means that logging is some cross-cutting concern, and we can push it through to all the RDDs or whatever. And then here's get partitions, override of get partitions. Was this something that we saw before? I thought, yeah, okay. I know we saw JDBC partition. Okay, so get partitions will take an array of partition. Is that right? Or it will return one? What's the syntax for it? Yeah, so it'll return one because we have no double arrow here, I guess. And that is, we're going to take the upper and lower bound, subtract them, add a big int 1 because their upper and lower bound, I guess, might be, the difference might be big. Bounds are inclusive. So this is how to, this is, I guess, avoiding a, what's it called? Off by one error. And then I'm assuming this is a Scala version of a for loop, from 0 until num partitions, basically from, if you're Python, range num partitions, essentially. For everything in there, we're going to apply a function, which is what this map is doing, which takes the index. So if this was just a for loop, this would just be, I would just be a variable here. Then we're going to do this computation on the lower bound, basically taking the lower bound and adjusting it by the partition times the length of what, I guess, length of a partition is essentially. I don't know where length came from. It came from here. So I guess this is the length of each partition, and we're dividing it by the number of partitions. Or maybe length is the total length of all of the stuff, upper minus lower. So this is, this whole thing essentially is the length of one partition. So that's the start. And then the end is basically kind of the same thing, except we're adding one here to say that we're starting, I guess, one off from where we left off in the previous computation, and then subtracting one just so that so that we're not off by one in our computation. And then we're going to return this JDBC partition of this stuff. And JDBC partition was what we saw up here. And I don't remember if I said it, but what I was wondering is whether this is essentially something that we're going to call recursively to help us chop up the job. And that seems to be exactly what's going on. And then compute, which I imagine is one of the fundamental, so we have overrides here, right? So I think these are the fundamental methods of an RDD. Get partitions, like how do we chop up the job? And that's on the RDD author to implement. And then compute. So how do we compute a job? So we compute given a partition and a task context. And I'm guessing a task context is kind of like a Spark context, but maybe specific to individual tasks. So you have like one Spark context, and somehow each task will have its own context that's potentially informed by that Spark context. And then it's going to return an iterator. Iterator of T, iterator of the type you passed in. And I think this means by default it's just a next iterator of T. And how do we implement compute? We take context, which is the task context, and we add a task completion listener with, I guess, the unit type. And it's going to be, the listener, I guess, is going to do a thing. This is essentially maybe like a callback that says, when the task completes, what callback do we execute? I think is what's going on here. And it says, given the context, just call close if needed, really ignoring what the value of the context is. So maybe close with needed is defined here, but presumably this is going to do things like close the database connection and clean up anything that needs cleaning up. 1 second here. Let me just make sure my my audio is good. Okay. All right. Okay, so then so that's what the task completion listener is doing. And then for we're going to get part, con, and statement. So statement is going to be just, we're going to take the SQL statement and somehow prepare it, passing in these type forward only, concur read only enums. Con is we're going to get the connection using the function that was passed in, and part is going to be the part as instance of JDBC partition. So what is the part? The part is, I guess, the partition that was sent in. This partition has a general type, I guess, because we're overriding a method of the RDD. So it has this generic RDD type, and we need to cast it essentially to the specific JDBC partition type that we're using here. What else? So then we set the URL to be, we take the connection and we get some metadata, we get the URL. I guess this is maybe where the worker lives. And if the URL starts with MySQL, then we might do some stuff, and we're looking at the MySQL source code in the next stream, which will probably start maybe around 11:30 now. And then if it starts with MySQL, we've got some commented out code, but it doesn't seem like, oh, okay, set fetch side is a MySQL driver specific way to force streaming results. So we're going to force streaming results. Otherwise, we'll set the fetch size to 100, which I guess will stream in other non-MySQL implementations. And then we're going to log some stuff, presumably to some like centralized logger, maybe just to somewhere on the worker node, I'm not sure. And then we'll set the lower and upper parts. Then we will execute the query and get the result. And then we're going to define this get next function. I think we're still inside of compute, right? Are we? Yeah, I think so. So inside of compute, we're defining this get next function. And it takes no, it doesn't take anything, I guess. It just returns the type T. And if the result has a next, I suppose, I guess if it returns anything, then we're going to call map row on the result. Otherwise, we didn't get anything back. So we'll just say we're finished. And we'll return null, essentially null cast to a T type, I think. And then we have this close function, which is presumably just going to close the database connection. And I think that's really all I wanted to see here. Should we look at create an RDD instance? That's maybe not so interesting. Okay, so given that, let's, I guess, see what Bard had to say. So RDDs, or resilient distributed datasets, are fundamental concepts in Apache Spark. They're essentially distributed collections of elements that can be processed in parallel across a cluster of machines. Here's a breakdown of their key features. So they are distributed, immutable. Once created, an RDD cannot be modified directly. Instead, new RDDs are created by applying transformations on existing ones. So this is a kind of standard functional programming sort of approach. They are resilient. Spark can automatically rebuild lost partitions due to node failures by recomputing them from previous ones. This ensures data integrity and robustness. We haven't seen this in the SQL one. Maybe we'll see if there's anything there. And then there are two main ways to work with RDDs. We have transformations. These are operations that create new ones from existing ones. So I think this is like the algebra stuff that I mentioned. Examples include filtering, mapping, grouping, and joining. Actions, these are operations that return a value to the driver program after performing computations on the RDD. Examples include counting elements, finding minimum, maximum values, and collecting data. Okay. All right. So is there a way to reconstruct? I'm not sure. I don't see anything here that, make sure that your data is, for example, properly duplicated. Like if you have if you have a single SQL server somewhere that it has your only copy of data, I don't know what happens if that goes down, if Apache Spark makes any determination about what to do there. Here's Hadoop. I think I don't know enough about Hadoop to know about its what's going on necessarily, but let's at least see if we can take a quick look at the compute and partition methods. We're taking, I guess, reasonable stuff like a broadcasted config. I guess you're going to broadcast the config because Hadoop itself is a distributed system, whereas something like MySQL, I think you have to work hard to distribute it in a horizontal way. So I guess there's a single endpoint that you have to hit and make requests to. So maybe that's why we're broadcasting stuff here and we weren't in the SQL one. We have input from format class. Maybe this is something about like what kind of format is stored on the Hadoop and stuff like keys and values and et cetera, et cetera. So what I want to see really is just def compute maybe. The split, I think, is named something else in the SQL one or whatever, but you take a partition, you take a context again, and then in this case, we're returning an interruptible iterator that is going to be an iterator of keys and values. And in what sense is it interruptible? I'm not sure. Maybe that's for like lazy evaluation or something, or like maybe it has like a coroutine logic. At any rate, we're going to set iter to next iterator. And then I'm not sure what this notation is doing, but maybe it means like after setting this, you do the following. We get the split as an instance of Hadoop partition, basically casting to the more specific type. Get the job config, do some stuff with metrics, and take the split and I guess do some, this looks like pattern matching in Scala maybe. And basically is it of type file split, in which case we do this input file block holder. Otherwise, we unset the input file block holder. And then we have some callback for get bytes read. So I guess once we read some bytes, we have some callback, and what we do depends on this file split stuff. We might look, I guess, in the Hadoop util to get some callback thingy. Okay, I think that's enough for me to see just some of the patterns for how these work. And then async RDD actions. These, I guess, are actions you can do on RDDs that are asynchronous, but we'll see what some of them are. You can do count async, which returns a future for counting the number of elements in the RDD. All right. So this is like, how many, if you want to know something like how many books did we sell in the last quarter, you maybe get a list of books back from each of the different machines, and then you count the total or something like that. Collect async returns a future for retrieving all elements of this RDD. So collect async returns a future. That's what it returns. What does it do? So we're returning a future action of sequence of T with whatever self with scope is. There's some sort of, I guess, like context or scoping thing here. And we're creating an array of the whose length is determined by how many partitions we have. And then we're going to submit a job of what? That takes the pair of index and data and returns results of the index. The index is this array thing, right? results of index, maybe this is at index, I'm not sure, is going to be equal to data results flattened to immutable array sequence. Yeah, I'm not sure. This is maybe, I don't know what this syntax is doing, but this is maybe, I don't know. For retrieving all elements. So this is maybe like the tail, and that's the head. We're like adding the data to the rest of the array. I'm not sure. It's doing something. And then we have take async, which returns a future for retrieving the first num elements of the RDD. So this is like in Haskell, I guess, like take 5 will return the first 5. And these are, I believe, lazily evaluated. Certainly they're async. But let's, I'll ask, are actions lazily evaluated in RDDs? We'll come back. And we have continue, which recursively triggers jobs to scan partitions until either the requested number of elements are retrieved or the partitions to scan are exhausted. So this is like maybe like co-recursion. Here's like a for each loop for each partition and so on. So that's not a ton. We don't see things like union. I wonder if we have we have the union RDD, so maybe we'll take a look at that. Let's take a look at union RDD. Get rid of Hadoop. Maybe subtracted. An optimized version of cogroup for set, difference, and subtraction. It is possible to implement this operation with just cogroup. So cogroup, I think, is another RDD. Did we open it? Cogrouped. The references to RDD and split index or whatever. What do you do? What do you do? Stores information about the narrow dependencies used by cogrouped RDD. But what is a an RDD? Here we go. An RDD that cogroups its parents for each key in the parent RDDs. So we have a graph structure here. If you recall, the resulting RDD contains a tuple with the list of values for that key. So for each key in the parent RDD, so we have the parents' keys. Oh, I get. I think you pass it in a bunch of RDDs, and those are the ones that it considers the parents. And we're just so if you have one RDD and the key of name is Bob and another RDD and the key of name is Jennifer, then I think what it's saying is that we're just going to return a tuple where name says Bob, comma Jennifer, that sort of thing. I'll assume that's mostly true. So let's look at subtract again. So it's an optimized version of cogroup for set, difference, / subtraction. And so this is basically what I figured it would be. So we have we have two RDDs, one of which contains stuff we want and one of which contains, I guess, only stuff we don't want. And and the first one might contain a bunch of stuff we don't want in addition to the stuff we want. And so by taking the difference, we get only the stuff we care about. And I guess let's look at the implementation. With this implementation, only entries from RDD1 are kept in memory, and the entries from RDD2 are essentially streamed, as we only need to touch each one to decide if the value needs to be removed. This is particularly helpful when RDD1 is much smaller than RDD2, as you can use RDD1's partition size and not worry about running out of memory. So this is like, you have some query like, who are the troublemakers in my class of 1,000 people? And the potential troublemakers are like Bob and Joe. And so you just need to read, you get the name Bob, I guess, and you start streaming names until you see that Bob is in the second list. And if he is, we decide he's not a troublemaker or whatever. And then you move to the next one. And I guess the optimization comes from the fact that if you have a small number of RDD1 entries, and then you only really need to defeat the assumption that it's not in the second RDD. But I guess if the entries are never in the second RDD, then eventually stream everything because you're checking something that doesn't exist, I suppose. At any rate, we have this subtracted RDD class, which has which has a class tag here, which has a class tag for K and V and W. I don't know if those are the parents or what. No, they're not. But we have RDD1, which is, I guess, a product of K and V, and RDD2, which is a product of K and W. So the K is essentially the keys for both. They have the same set of keys, and then the RDD1's values are V, and RDD2's values are W. It looks like. So we have this get dependencies thing, which we're overriding. So RDD dependency of T1 and T2. And I'm not sure what it means to pass this thing in here, but the implementation is if the RDD dot partitioner, so we're passing in a single one, right? Yeah, so this is just the argument of the function. So we're passing in an RDD that I guess is probably like a subtype of the product of T1 and T2. Essentially the Cartesian product. Product 2, I'm guessing just means a product with two elements, but maybe we'll check out the Cartesian product one. And I guess we call on the single RDD that was passed in, but the RDD seems to be like a Cartesian product. We set the partitioner, we check if the partition is equal to some part. I'm guessing some is like part is optional, and some means it's like the Haskell, it's like the Scala version of Haskell's just. It means it's not the nil value of optional. So I guess if the partitioner is like populated, then we return a new one-to-one dependency of RDD. Otherwise, we do this shuffle dependency too, and I'm not really sure what that does. Then we return sequence of some stuff, which again, I don't know what it does. But get partitions, we'll just create this array, iterate over it. We have a for loop this time. And array, this must be the indexing notation. I don't know if this is Scala or if this is like a special kind of array that uses this notation. But array of I guess, is equal to a new cogroup partition with the index I and whatever sequence of RDD1 or RDD2 is, and then we're going to zip with index. So this is some like zipping, list zipping, and I guess mapping the list zippy stuff. Okay. So we have some zipping, and we're passing in a function that tells you how to zip. And that function is going to take the RDD and the J, where J is, I'm not sure. I guess that whatever the second argument is, and looks at the dependencies of J. And if it's a shuffle dependency, then we return none. Otherwise, we return some new cogroup split dep with RDD1, the index, and the RDD partitions at the index. So I'm not sure really what that does, but I think morally speaking, what it's doing is it's somehow kicking out the, what it needs to do, I think, is kick out partitions that don't contain the stuff that we need from RDD1. And I'm not sure if this is what's doing it, the shuffle partition stuff. I'm not sure what the shuffle dependency means, but I think that's more or less what's going on. And then to compute, you take a partition in a task context, and we're going to return again an iterator of keys and values, and then cast to the more specific type to the partition, and get a J hash map, which must be a some Java-based hash map from keys to array buffer of values. And then we've got this get seek thing that takes in the keys. It's going to return an array buffer of values that we're going to get the thing from the map. And if it's not null, we return seek. Otherwise, we set it to Otherwise, we like put it in the map and return seek. And that's all we do. Oh no, and then this is still within the compute function, right? And then we have integrate, where we look at the dependencies. If there's a one-to-one dependency, we do some stuff. If there's a shuffle dependency, we do some other stuff. And then the first step is RDD1, add all values to the map. So I guess this is going to add all values to the map. The second one is RDD2, remove all of its keys. So whatever this integrate function is, this is some like functional thing in the types of RDD, but I think this is the logic that's going on. We're going to add everything from RDD1 and then remove everything from RDD2, just like you would do, I guess, with a Python set if you were implementing set difference on your own. And then we're going to return the map converted to an iterator, essentially, because that's what the compute function needs to return. All right, so I think that's a little bit of RDDs. Should we look at shuffled RDD? Let's at least see what it says. The resulting RDD from a shuffle, e.g. a repartitioning of the data. And we're going to pass in the parent RDD, the partitioner used to partition the RDD, the key, the value, and in some way, I guess, of combining it. And I guess it's on the implementer to decide how to implement it. Cartesian should be just the product of two RDDs, essentially. We'll ignore this. Block, I'm going to guess, is like block storage. Get block manager, block ID. Are we importing anything? Yeah, so block storage, I assume. Binary file, we'll ignore shuffled RDD. I think we opened in rdd.scala. So let's look at rdd.scala. This is going to be the main file. How are we on time? We're doing okay. A resilient distributed dataset is the basic abstraction in Spark. The basic abstraction, I'm glad, this seems to confirm my theory that this is where to be, represents an immutable partitioned collection of elements that can be operated on in parallel. This class contains the basic operations available on all RDDs, such as map, filter, and persist. In addition, the pair RDD functions contains operations available only on RDDs of key value pairs, such as group by and join. The double RDD function are things that are only on doubles. And sequence file are the ones only on sequence files. Internally, each RDD is characterized by 5 main properties: a list of partitions, a function for computing each split, and we've seen these in the implementations, a list of dependencies on other RDDs, optionally a partitioner for key value RDDs, e.g. to say that the RDD is hash partitioned, optionally a list of preferred locations to compute each split, for example, the block locations for an HDFS file. All of the scheduling and execution in Spark is done based on these methods, allowing each RDD to implement its own way of computing itself. Indeed, users can implement custom RDDs, for example, reading data from a new storage system by overriding these functions. And there's a Spark paper. I guess this is like a white paper. That's not so surprising. So yeah, from Berkeley originally. All right, well, we'll read this later. Okay, so here's the abstract class, which should look familiar to us now. We have the private variable _sc, which is the Spark context. We have the dependencies. I'm not sure what seek is. So let's see if seek is a Scala thing first. Yeah, the universal equality method. So seek, I guess, is the base. It says it's the base trait for sequence collections. I don't know what I think it gets anything that's listy. Like it has this, you can keep pulling stuff off of it. Difference between a seek and a list. In Java terms, Scala seek would be Java's list, and Scala's list would be that of Java's linked list. Seek is a trait which is similar to Java's interface, but with the equivalent of up-and-coming defender methods. a defender method. And then list is an abstract class that is extended by nil and colon, which is maybe like cons, which are the concrete implementations of list. Yeah. Okay. All right. So essentially a list. All right. And so we check if class of RDD is assignable from some runtime class thing. And we warn, I don't know what that means, but we'll ignore it. We do some basic checking for the Spark context. We grab the config essentially from the context. Here we construct an RDD with just one-to-one dependency on one parent. I'm not sure why, but I guess that's the thing we do. So here's the developer API implemented by subclasses to compute a given partition. And so we've seen these before. So one is compute, which takes the partition in the task context and gives you back an iterator. Another is, where are we? Get partitions. Returns the set of partitions in this RDD. I guess each RDD is immutable and it has, it already knows what its partitions are. You can't like repartition an RDD. So I suppose this is at creation time, I guess, just by virtue of the fact that the function is implemented, perhaps. Although I don't know if it'll fail if you have like a random function. Who knows? Get dependencies. That'll return how the RDD depends on its parents, which is a sequence of dependencies. So I don't know if the ordering matters. It will only be called once, so it is safe to implement it in a time. You see, having a time-consuming implementation, that's good. Get preferred locations. This is for like localization or like maybe affinity, you might call it. And then a partitioner, which is also optional. So this is optional. This is not using the optional type, but it's essentially a seek, which we're thinking of as a list, which is nil, which is basically optional for lists. And then we have the context that created the RDD, a unique int, a unique ID for this RDD. I guess the Spark context cares about it. A friendly name, which is transient. And you have a setter for the name, and you might be able to persist it somehow to storage and whatever these other persist implementations are doing. And you can get the storage. There's a lock for all mutable state of this RDD. I thought it was immutable. Well, what does this say? I'm not sure. This raises, yeah. So the reason I think that they're immutable is because of threading. So you don't have to, the more immutable they are, the less you have to worry about threads monkeying with each other's RDDs. And then the rest kind of looks like getters and setters and that sort of thing. Maybe these are like default implementations so that you only have to implement one or two of the methods. Okay, so that's RDDs. I consider that a reasonable amount of detail. Here's shuffle. I don't think we're going to be able to do shuffle justice. So with regrets, I'm going to just close it out. Scheduler. We can at least look what's here. We have a DAG scheduler, which is presumably going to build a DAG. We have things like active job, which is probably just some essentially class data objects for keeping track of which jobs are active. We have health tracker, which is presumably like an endpoint you can read to check if something is healthy. Things like job waiters, map status, merge status. Pool is presumably going to be like a thread pool or a process pool. A scheduler backend. I'm kind of curious if there are multiple scheduler backends and if there are multiple scheduler algorithms. And then we have just things like, a task has some implementation, which I think probably from our point of view, in terms of like, if our goal is to learn about how these systems are built, then I think that like the actual implementation of the job or the schedulers only really matters in the sense that once we see a few of them, we'll have a sense of what schedulers are about. But the actual implementation might be something that was different 5 or 10 years ago and might be different in the future as hardware changes or whatever. So unless you're like tuning Spark right now, it may not be the most important thing to like really understand how those implementations go. Here's DAG scheduler. I'm just kind of curious to give it a quick once over. This is the high-level scheduling layer that implements stage-oriented scheduling. It computes a DAG of stages for each job, keeps track of which RDDs and stage outputs are materialized, and finds a minimal schedule to run the job. Minimal in what sense? Maybe least wasted work or something. Then submits stages as task sets to an as task sets. Task sets. To an underlying task scheduler implementation that runs them on the cluster. Okay, so the job of this DAG is to build a DAG, of this DAG scheduler thing is to build a DAG, and then given the DAG, produce task sets, which I think we can think of as probably lists, although they might technically be sets. And then they're handed off to some task scheduler that's just going to take the tasks and probably in a relatively dumb way, just hand them out to workers. The task set contains fully independent tasks that can be run right away based on the data that's already on the cluster. Okay, so I think this is consistent with my thought that maybe the task scheduler is relatively dumb. It doesn't seem to need to care what's on the cluster because once it's handed the task sets, it seems like that's taken care of. Spark stages are created by breaking the RDD graph at shuffle boundaries. What's a shuffle boundary? I have no idea, but we have this big graph. We're going to cut it up. And I guess the shuffling information is going to tell us, can we cut it up in a useful way so that each maybe subgraph after the cutting is computable by a single machine. RDDs with narrow dependencies like map and filter are pipelined together into one set of tasks in each stage, but operations with shuffle dependencies require multiple stages, one to write a set of map output files and another to read those files after a barrier. So I'm assuming barrier is going to be like the barrier in CPU. So we have something that says we have to wait until some stuff is done. In particular, the files are written. And after that stuff is done, we can begin the next stage. In the end, every stage will have only shuffle dependencies on other stages and may compute multiple operations inside it. Okay. The DAG scheduler also determines the preferred locations to run each task on, based on the current cache status, and passes these to the low-level task scheduler. So somehow we're going to look at the caches. What do the workers know about? Which chunk of data do they have, essentially? And we're going to use that to decide who should compute what. This is like when you've been working on if you're working on a bunch of features in a team, right? Maybe you've been working on feature X for the past 3 weeks, and something new needs to happen on feature X. It's easier to give you the new thing on feature X than something on feature Y, because otherwise you have to unload all the X stuff and load all the Y stuff into your mental RAM or whatever. When looking through this code, hey, look, this is maybe the first time in the in the history of Answer Everywhere where we have a comment that directly addresses the fact that somebody might be reading the code. I guess that's always implicit, but this is really nice. Line 79 of dagscheduler.scala. Maybe we'll blame to see who wrote this. And I'm not sure if blame will pull up the original author, but this guy. Maybe. Mattel's? Possibly this guy from San Francisco. Matei. Was that his name? All right, well, whatever. Okay, so when looking at this code, do what? There are several key concepts. Come on, GitHub. There we go. Jobs, stages, tasks, cache tracking, preferred locations, and cleanup. And then we get a snippet about each one of those. Jobs are represented by active jobs, the top level items submitted to the scheduler. Stages are sets of tasks that compute intermediate results. I wish I could link here, but maybe, I don't know, maybe that's a lack of GitHub feature, where each task computes the same function on partitions of the same RDD. Okay, so we're not going to look too much at this code, despite that wonderful comment, because we're closing in on time. But this is going to build the DAG and do all the things it said it was going to do. Scheduling algorithm. I'm mostly just curious what different algorithms we have. I guess scheduling algorithm is a trait, which is basically an interface for a sort algorithm. And this is basically a comparator. You take two schedules, two things that are schedulable, and you return a Boolean. I don't know if true means 1 before 2. I guess it probably means 1 before 2. I don't know. Or otherwise, it probably means 2 before 1. We have FIFO scheduling, which should just be first in, first out. So let's see. So we're getting the priority. So I guess the schedulables have priorities. And we're taking the difference. So if this is positive, then S1 has a higher priority than S2. S2. But sometimes higher priority means less priority. Like in some bug trackers, for example, P0 is the most important. And then P4, P5 would be people are barely going to get to it. So I'm not sure if bigger priority is better or vice versa. But at any rate, if they have the same priority, then we get their stage IDs and we set result to check whether one stage is before the other. Otherwise, we're returning whether the result from this match was less than 0. And again, I don't know semantically whether that means to do S1 first or to do S2 first, but I guess this tells us, right? Because I think we want the stage with the lower ID to go first. And so if stage 1 it comes before stage 2, then this will be negative. And so I guess negative means negative, I guess, is probably false. So that means we return false if S1 is first, I guess. I'm not sure. All right, and then we have fair scheduling, which is going to compare these two. I don't know what min share is, but we're getting the min share, the running tasks for the two schedulables, whether they are needy. I guess, okay, needy is defined as if the running tasks are less than the min share. Maybe this means that we're running fewer tasks than we can handle, so we can so you can give us more tasks potentially. And then we have this min share ratio, which is we're just going to take the number of tasks, cast it to a double, and then divide it by the maximum of min share in 1. So this is, I guess, to prevent, if min share is maybe an integer, this is maybe to prevent dividing by 0. And then we have the task to weight ratio, which is we're just going to take the number of tasks and whatever the weight is and divide them. And then the fair scheduling, this is the only other algorithm that's here. We're going to set compare to 0. If S1 is needy and S2 is not needy, then we'll return true, which I think in this context should mean that S1 goes first. So maybe I was wrong before. Otherwise, if S1 is not needy, but S2 is, we'll return false. Otherwise, if they're both needy, then we look at the min share ratio, I guess, and smallest min share, I guess, wins. Otherwise, if they're not both needy, and I guess if we're down here, then neither is needy, then we're going to look at the task to weight ratio, and that will be compare. And if compare is less than 0, we return true, which I think based on this means that S1 wins. Otherwise, if compare is bigger than 0, then we return false, which I believe means S2 wins. Otherwise, we just look at their names. And I guess this is like supposed to be a tiebreaker, but like a deterministic tiebreaker as opposed to rolling a die, which is not the worst thing, but now your performance seems to depend on what you name your stuff. And there's that, there's that rule that like people will eventually depend on everything that you all observable behavior of your system. So I'm not sure if you want people to like abuse that, but maybe the names are semantically meaningful already. I'm not sure. All right, so those are the scheduling algorithms we have, and then we have the scheduler backend. And I'm not sure what this is going to do, but a backend interface for scheduling systems that allows plugging in different ones under Task Scheduler impl. We assume a model where the application gets resource offers as machines become available and can launch tasks on them. So like as you add a machine, or a machine like stops being grumpy or whatever, it will say it's ready to do work. And I guess you will be able to schedule based on that information, which is interesting, but maybe we're not going to look too much at it. So that's Apache Spark. I'm going to stop there. That's really interesting. I like I said, going in, I didn't know much about it. The code is super clean, even though it's Scala, and I don't know Scala. Everything was, it's really clear what almost everything did. There was some stuff maybe in the beginning or late beginning there, where I wasn't quite sure what the types were up to. But even there, like they managed to do a lot of relatively abstract stuff using really readable code. And it's clear from at least that one code comment that they expect people to read the code, and it's optimized for people coming in and reading it, which I think in the long run probably helps a lot with having a community who's willing to like improve, optimize, and that sort of stuff. Because the easier it is to read, the easier it is for newcomers, especially newcomers with a lot of experience, to help out. So that's Apache Spark. Thanks for watching. In a few minutes, I'll go ahead and we'll take a look at MySQL.